We can also try to understand reliability by thinking about the analysis of variance, in particular the repeated measures ANOVA and the distinction between within-group variation and between-group variation. The distance between any individual score and the total mean can be seen as the distance between it and its group mean plus the distance between the group mean and the total mean. But here the group is the item on the questionnaire. The following equations show what happens when we square those differences and sum them up. This slide shows us how total variation, or the total sum of squares, is broken up into different components using repeated measures ANOVA. We follow the route through variation within items and break that down into variation between respondents' means and the grand mean and variation error. The variation between the item means and the grand mean will only differ from 0 if the means of the items differ. If this happens, we will get additional variation in the sum scores. ANOVA needs to remove the variation caused by differences between the means. This is rather like removing the slope in regression so that we can examine the residuals. Having eliminated the variation between the item means and the grand mean, what's left is variation between respondents. We would expect there to be differences between the respondents to the questionnaire, but we don't want variation between items on the questionnaire. The subjects or respondents are now treated as if they were groups, so we need to know how much variation is generated by the mean differences between the respondents and how much error is unexplained. This is the important bit to understand. If each respondent responds entirely consistently, then the means will be equal to their scores for the items. There will be no variance around the means, therefore no errors or residuals. Now we can use this formula to find alpha. We have to find the mean of the squared differences between the average scores for each respondent and the grand mean. That is the denominator here. And we have to find the numerator, which is the difference between the summed within item variation and the sum of the squared differences between the average scores for each individual and the grand mean divided by the remaining number of degrees of freedom. That's quite a mouthful, so let's see how it is actually done using the example that we have seen. Remember, we're trying to see how much of the variation between respondents is inconsistent. Now concentrate on the last column of the table. That shows us the squared differences between the mean scores for individuals and the grand mean. Summing these squared differences, we get 26.5. For the formula, we have to divide that number by the number of degrees of freedom, which in this case, that number is 6, because there are 6 respondents. So that makes 5 degrees of freedom, giving us 5.3. As there's no variance between the items, the sum of the within item variation, not variance, is also 26.5. So the error is equal to 0. 0 divided by the remaining degrees of freedom, that's 10, keeps the numerator at 0. Alpha is 1 minus 0, giving 1. You can see why the means of the items must be prevented from influencing the conclusions. Here, all of the item means and the variances are the same, but the respondents' scores are clearly different. The scores here show entirely consistent responses, so we get an alpha of 1. But we could also have got these scores. Notice how the item means and variances are the same, so there is no between item error. What has clearly changed is the information in the last 2 columns. Alpha is now almost 0, which shows that the responses are inconsistent. And in slide 17, we can see that the item means and variances are still the same, but now the inconsistencies are so large that alpha is negative. That is because the mean of the squared errors is larger than the mean of the squared differences between the respondents' means and the grand mean. In other words, we are getting these different alphas even though the item means have not changed. But we could have a situation where the item means differed, but the variances remain the same. That would introduce a confounding element, as it would inflate the total variance. That's why when calculating alpha, between item errors are ignored. To illustrate this, let's take a look at perfect consistency again. Now keep your eye on the last 3 columns of the table. Now look at this slide. By systematically adding 1 to item 3, the grand mean increases to 3.17, but the variance for each item remains the same. So we have added 4 to the total sum of squares. This is ignored and alpha is still 1. This was done using Excel, but you can see that this looks like an ANOVA table. The only information you need here is the mean squared errors and the mean of the sum of squared differences between respondent means and the grand mean. Now look at this slide. This was also done using Excel, but this is an ANOVA printout. Cut through the excess of information and you'll find the mean squares you need. The error term is not 0, but it is very close, and this happens because of the way Excel works. The degrees of freedom are also evident. I found this on lynda.com, where it said Excel has a tool for the repeated measures ANOVA, but it's hiding out in the analysis tool pack under a different name, ANOVA 2-factor without replication, which is very strange because I think this is obviously replication, but anyway. Here's another example. I've given Zach a score of 5 on item 3, so the mean squares have changed and alpha has dropped to 0.961. But here we find the same information, so you don't need sophisticated programs to find alpha.